everybody. Today we're going to be looking at applications of exponential functions, basically just a bunch of examples. So there's another video explaining what all of the values mean in an exponential function, and now we're just going to be applying that with some examples. So first we'll start with the half-life example. So a 200-gram sample of radioactive polonium-210 has a half-life of 138 days. Okay, so let's take a look at this sentence. So the half-life is 138 days, and it started as a 200-gram sample. Okay, this means that every 138 days, the amount of polonium left is half of the original amount. Okay, so the mass in grams after t days is modeled by this function. So let's explain each part of the equation and relate it to the situation. So the 200, where does that come from? Well, that's the A value, which is 200, and that's the original amount. Okay, the B value is a half. Okay, this is the rate of decay. Okay, so remember B is equal to 1 minus the rate. So the rate is a half to get a half. So that means it's decaying by 50%. Okay, now the T over 138 might be giving you guys a little bit of some questions. Why isn't it just T? Why is it T over 138? Well, let me explain this to you first before I write anything. This is the number of doubling periods, okay? But you want to put T in days. So it takes 138 days for this half to run its course. So for it to truly be at 50%, it takes 138 days. So if you put in T equals 138, then you get that exponent is equal to 1, right? Because you get 138 over 138. That makes sense because that means it's gone through one of the half-rate cycles or half-life cycles. If you have only gone through, let's say, 50 days, that's not even, or that's just over a third of one half-life. So you don't want to put in T equals 50 without the denominator of 138. If this was just T, and you put in 50 here, that would represent 50 half-lives being completed, okay? And that wouldn't make sense. 50 half-lives is like if you take 138 days times 50 and have some huge number of days. So you want the percentage like this so that you can let this be number of days. So what part of 138 have we gone through? So think about the number 200. If you put 200 in, then that will be about 1.5, not quite, half-lives that have been completed. So that's why you want the fraction there. Okay, if you're having trouble understanding that, make sure you come and see me. It's a really, really important thing to know when to use a fraction there and when not. So this is the number of periods in T days. This represents and I'll put it in quotes, percent, or the fraction, toward 138. If it was just T, then T equals 1 would represent 138 days. Okay, so if you just did this whole thing to the power T, so 200 times 1/2 to the power T, then T equals 1 would represent the time it takes to do one half-life. So that would represent 138 days. So that would be tricky because if I asked you, okay, how long would it be after 200 days, you'll have to see like, well, how do I represent that as a decimal using where 1 is represented by 138. It's easier to put the fraction because now we can just put the number of days in without having to come up with a decimal. The fraction is set up for us. Okay, so analyze that. Make sure you understand all the parts of the equation, because later you will be expected to come up with equations on your own. This time it's given to you. So now they want us to do two things. First, determine the mass after 5 years, and then they want us to know how long it takes to decay to 110 grams. So determine the mass that remains after 5 years. Well, we have T has to be in number of days, so we have to take 5 years times 365. Okay, so we're just assuming 365 days in a year, so we're not doing leap years. So that gives us 1,825 days. So we just need to find M at 1825. Okay, make sure you're using the function notation. And now you just sub in 1825. So 200 times 1/2 to the power 1825 over 138. Okay, now I want you to actually get your calculator out and do this to make sure you're putting it in your calculator properly. Okay, the 1/2 has to be in brackets, so I would do 1/2 to the power, and then in brackets put 1825 divided by 138. Okay, find this and then just multiply it by 200. Okay, so you should get 0.021 grams as your answer. Okay, so please try that in your calculator to make sure you know how to do that. If you're not getting this answer, we'll work on it together to make sure you're using your calculator appropriately. Okay, so this means that after 5 years, there's 0.021 grams of the polonium left. All right, how long does it take for this 200 gram sample to decay to 110? Well, first let's think about this. Let's estimate that. So if it's gone from 200 to 110 grams, has it gone through a full half-life? And if so, about how many half-lives has it gone through? Well, you should reason here that it hasn't quite gone through an entire half-life, because half of 200 is 100, and it hasn't quite gotten that low yet. So our T is going to be less than 138 days because it hasn't completed its half-life cycle yet, but it'll be relatively close because we're getting close to 100. So think about that estimation first, okay? Because you need to make sense of what's going on, not just memorize the steps, okay? You need to understand what's actually happening. So we'll say, so T has to be less than 138, but we think it's going to be close. Not like super close, like 135, but it's not going to be 20, for instance. Okay, so we have to set up our equation. What is it? 200 bracket 1/2 to the T over 138 equals 110. Okay, so we can divide both sides by 200. And that gives us 0.55. But guess what? That's as far as we can go. Okay, there is no way that we can actually go any further. We cannot multiply both sides by 2 because this isn't being divided by 2. This is actually the base of an exponential function. So that operation, you can't do that. It wouldn't make any sense. You can also not multiply both sides by 138 because this is in the exponent. So now you're left with having to guess and check. Okay, so we need to find the closest integer that will give an answer as close to possible as 0.55. So that's why estimating is so important. You don't want to just start throwing in random numbers for days. You want to start at something realistic. So I encourage you to start maybe at like 100. See, is that too high or too low compared to 0.55? And then if that's way too high, for instance, then put in 130. and then you'll notice that's too low. So you keep trying and trying until you finally get t equals 119 is the closest integer. That's the one that's the closest, okay? It's closer than 118, 118, or 120. So one guess is never enough. It's never good enough to just guess once. You have to get the one that's closest, not one that looks close, but you have to give me the answer that's closest, okay? So play around with it in your calculator. You'll see what different values of t will give you, and you can confirm for yourself that 119 is the closest, okay? But in grade 11, that's how you have to solve those problems, is by estimating, okay? Next year in grade 12, we'll learn how to find the exact value without having to estimate. But estimation actually allows you to really understand what's going on with exponential functions and, you know, use your brain a little bit. Nothing wrong with that. It's great, a little brain work, right? Okay, so here is something that is given with a table of values. So it's population growth of some frogs. So you'll notice that the years are increasing by a constant amount, 1 year each time. And the population is, it's going up by 80, and then it's going up by 96, and then it's increasing by 115, and then it's increasing by 138, and then 166. So there's definitely growth here. So we want to come up with an equation that represents a function of time in years. So we know that our a value is going to be 400. That's our initial value. Okay, but it's this b value. We know it's going to be 1 plus r because we know it's growth, since the population is increasing. But we have to find this rate. So the rate is just the percent increase. Right? So it's going to be how much has this increased over a year in percents. So the population of n plus 1 minus the population of n divided by the population of n. So in this case, 480 minus 400 divided by 400. So it's gone up 80 from 400, so that's a 20% increase. Okay, that would give you 0.2. So therefore, your b value is going to be equal to 1.2, 1 plus your rate. Okay, and then we'll say t will be year t. We don't have to do any fraction because this is just, it's 20% every year, okay, every 1 year. So we don't have to do any fractions. So we can identify our variables. So let p at t represent population after t years. So p at t equals a, so 400, bracket 1.2 to the power t. Okay, so our a value is our initial value. This is 1 plus our rate, and then this is the time period. All right, when will the population have tripled? So you need to set this up to triple the population. So we started at 400 frogs. So triple that would be 1,200 frogs. Okay, so we have our equation. When will it be equal to 1,200 frogs? Or in other words, when will 1.2t be equal to 3? I just divided both sides by 400. So, do some estimation, okay? Pause the video, try this in your calculator. Your answer should be t equals approximately . Sorry, I know that answer is not correct. I'm looking at my answer and I'm like, that is not right. I'm gonna do some estimating too. Okay, so I think you should get t to be approximately 6. So after 6 years, I'm going to double check that that makes sense. So 1.2 to the power 6 times 400, yeah, is almost 1200. It's 1194.3936. So that's right. That dot means approximately. So it's about 6 years for this population to triple if it's increasing by 20% every year. Okay, so here's a new question. It's just all words. There's no table of values. So let's interpret this within a function. So a new car costs $24,000. It loses, so when you see loss, you should think of exponential decay. It loses its value each year. This is known as depreciation. Determine the value of the vehicle after 30 months. So we want to let